Namaskar, hello, and a very warm welcome to CIET NCERT's live phone-in interactive program. I am Tanvi Khurana, and this is a physics class for all the students starting in class 11th. And the topic that we are taking up today is simple harmonic motion, and this is the first part of this topic. You can see the topic on your screens as well. With this, we are taking up the first part, like I said, and we are going to raise questions, doubts, and if you also have any queries, then please reach out to us. Feel free to call us on our number, that is 8800440559. And if you want to email us, the email ID would be dth.class11@ciet.nic.in. It's being written on your screens as well. Apart from this, you're watching us on PME Vidya channel number 11 and also on our YouTube channel, that is NCERT Official. In the live chat box, you can raise your questions, queries, and we'll definitely try to take them up. Till 3 o'clock, we have an expert with us and she'll be more than happy to answer all your doubts. For now, let me please introduce you to our sign language interpreter, and she is Naina. Along with Naina, we have one more interpreter, Dharna. She'll be also joining us in this program. So, both of them would be interpreting each and every word that we are going to discuss in this particular program in the form of sign language so that it will be helpful to all of you. Now, let me please introduce the guest for today. We have with us Miss Pushpa Tyagi. Ma'am, a very warm welcome to you.
Namaskar.
Namaskar.
Thank you very much.
Thank you so much. Ma'am is a former PGT in physics from Kendriya Vidyalaya and Sanskriti School, New Delhi. So, let's begin this conversation without further ado, and let me ask ma'am, what is it that we are going to discuss in this particular program? Can you just give us a little brief about it?
In this today's program, we are going to discuss about simple harmonic motion. As you know, simple harmonic motion is a long chapter. So, we have divided this chapter into two parts. So, today I will be taking only the first part of simple harmonic motion, that is mainly the kinematics of simple harmonic motion I will be discussing today.
Okay, so shall we begin, ma'am? I can see that you have a presentation prepared. Would you like to show us the slides and maybe explain a little?
Yeah, I'll definitely begin. Now, before I begin with simple harmonic motion, I would like to ask you first, how do you come to know that a body is in motion?
When the position of the body changes?
Right. Now, how do we come to know that the position of the body changes? For that, actually, we need to first decide a reference object. Okay. So, in this room itself, we want to see if an object is changing or its position. We have to see its distance from the wall. If its distance from the wall is changing, that means the object is moving. It is in motion. Now, the next question which comes is, what are the different types of motion? Now, the different types of motion, the first one which I have mentioned here is translatory motion, and second is rotatory motion. Now, what is a translatory motion? That is the first question. And now, as you know, so far whatever you have been studying was either about translatory motion or about rotatory motion. Translatory motion is the one. Now, if I have this object, that is a pen with me, if I move this object like this, if I move this object from one place to another, the object as a whole is moving from one place to another. Now, when the whole object moves from one place to another, we call it as the translatory motion. Second one, the rotatory motion, is if I take the same pen and fix its one end and apply force at the other end. Now, if you see, one point of the object is fixed and the rest of the particles are moving. So, this is a type of rotatory motion. Now comes another type, that is called the translatory motion. That is the rotatory motion or the simple harmonic motion. Here I would like to correct myself. First, let's study something about rotatory motion, and then we'll go over to the next topic. Now, what is special about rotatory motion is, say for example, this pen I am rotating along a circular path. So, it completes one rotation and comes back to the same position, and then it keeps on moving. Another example of rotatory motion is motion of the blades of a fan. The special characteristic of rotatory motion is that these particles repeat their motion. They complete one rotation and then they start another rotation. So, we say the rotatory motion is periodic in nature. Now, when we say it is periodic, that means it is repeating itself after a certain interval of time. So, this kind of motion, they are called periodic motions.
Ma'am, let's just talk about a few examples regarding the periodic motion, shall we?
Yeah, definitely we will.
Okay.
Now, the first example which I gave you is the motion of the blades of a fan. Now, if we see about the swing, you all must have seen a swing. Swing also repeats its motion after a certain interval of time. It goes from one end to other end, then it goes from that second end to the first end, and then it repeats its motion. The example of the motion of a swing is also a periodic motion. Okay. Now, this time which this body takes to complete one oscillation, that is what is called its time period. That is the time taken by the body to complete its oscillation, or the time after the motion repeats itself, that is called the time period. Now, as it is a time, so in what unit will it be measured? You must be wondering. The unit, of course, is second, and it is always written as S, not a capital S. It has to be a small s in small letters. Okay. Now, another kind of motion. Let's see the case of a swing. What's the difference between the motion of a swing and the motion of the blades of a fan? Motion of the blades of a fan are also repeating itself after a certain interval of time. Motion of the swing is also repeated after a certain interval of time. Now, in this case, in the case of a swing, what happens is body moves back and forth. Body moves to and fro about a certain position. That position about which it moves to and fro, that is called its mean position, or it is also called its equilibrium position. Okay. Now, some examples of oscillatory motion, as I also told you, gave you two examples, motion of a swing and motion of the blades of a fan. Now, the difference between them is that motion of a swing moves to and fro, whereas motion of the blades of a fan is not to and fro. It completes one oscillation, then it doesn't move to and fro. It doesn't come back to the same position again and again. It doesn't move back and forth basically. So, motion of a swing is an example of an oscillatory motion, and after this we will also study the special type of oscillatory motion. But now for the time being we can say oscillations of a swing is an example of oscillatory motion. Similarly, oscillations of a mass suspended from a spring, whereas the other end of the spring is attached to a fixed rigid support, is another example of oscillatory motion. Here I am going to show you the motion of a mass attached to a spring. Here we have a spring. Actually, in ideal situation, this end of the spring should have been fixed. It should not move. Here I am trying to keep it fixed with the help of my hand. Now, this is the mass which is suspended. I pull it slightly and leave and see what is the type of motion it executes. See, it is moving back and forth. It is going away from that position, coming back to same position, overshooting, coming back and overshooting. See, once again you can see.
But ma'am, when it will stop at the same position from where you left.
Yes, definitely it will stop at the same position.
Okay.
That is because that was the position where there was no force acting on it. So, ultimately it will stop at the same position.
Okay. Ma'am, can we call oscillatory motion as vibratory motion?
Oh, yeah, that's a very good question you have asked. Now, what is the difference between oscillation and vibration? The term oscillation is used, they represent the same type of motion, that is to and fro motion. Oscillation is used when the body does not oscillate very fast. If the oscillations are fast, then it is called a vibratory motion. The motion of a swing is not a fast motion, so we call it as an oscillatory motion. Now the motion of the atoms in a solid or in a liquid or in a gas, that is called as the vibratory motion. That is the basic difference between oscillatory motion and the vibratory motion.
Okay.
Okay. Now let's go over to the next example, motion of a pendulum. Now how does a pendulum look like? You must have seen in that old grandfather's clock, that is, there is something which is moving back and forth under that spring. Now a pendulum basically consists of a bob, heavy mass, attached with a string. String should be weightless, in ideal situation, and it is suspended from a rigid support. The shading which I am drawing here represents it is a rigid support, it is not moving. And this bob, this becomes a pendulum. It is exactly like a swing only basically. If I pull it to one side and leave it from here, it will start moving from here, come back to this position. When it comes here, it will overshoot this position, come to this position, this side, and stop momentarily, and again come back to the original position. This will also oscillate. The motion of the pendulum, that is also called oscillatory motion.
Okay. But ma'am, nobody is putting any force on it, on the pendulum.
Yes, nobody is putting any force on it. Actually, what happens is, the moment we pull the pendulum, bob of the pendulum, to the other side. See, what happens is, it was originally, its center of mass was at this position.
Okay.
Now, its center of mass has been raised. That means its potential energy has increased, which you have done in the previous chapter of work, energy and power. It has a potential energy now, and potential energy will be mg into h.
Okay.
The moment you leave it from here, because of gravity, it begins to move down, because it has already been raised by height h. So because of gravity, it starts moving down. As it moves down, it comes to the original position. Now the moment it comes to this position, there is no force, but it has already gained some speed. Because of inertia, it will not be able to stop, because to stop an object, you again need a force. You have done in the chapter 5, that is the laws of motion. So it will overshoot. The moment it overshoots and goes to this side, again it begins to raise from its position. It begins to rise from its position. So again it gains potential energy. When its velocity becomes 0, that is entire kinetic energy is converted into potential energy. It will momentarily stop here and again begin to move, oscillate.
Okay.
So basically it is moving because of conversion of potential energy to kinetic energy and vice versa. Okay. Now let's go for another main special point. Here what it says is, look at the point what is written here. Every oscillatory motion is periodic, but every periodic motion need not be oscillatory. So for example, I told you the motion of the blades of a fan or motion of earth around sun. Motion of earth around sun is also periodic. It repeats its motion after 24 hours, you know. This is periodic, but earth doesn't move back and forth. It keeps on moving in the same direction. It doesn't change its direction. So motion of the earth around sun is periodic, but it is not oscillatory. So all periodic motion need not be oscillatory, but all oscillatory motion have to be periodic in nature.
Okay.
This is the main point you must keep in mind. Okay. Now, as I told you about time period, time taken to complete one oscillation, that is called the time period. Now, suppose an object take 5 seconds to complete one oscillation. How many oscillations has it completed in 1 second? That will definitely be 1/5. The number of oscillations completed in 1 second is called its frequency. And frequency के लिए we use the symbol nu. It's a Greek letter. Somewhere you will also find a symbol F written for it, but all these symbols can be exchanged. The formula for frequency then becomes frequency is equal to 1 upon time period. That is and time period is always represented by capital T. Now, what is the SI unit of frequency? As it is 1 upon time period and time is measured in second. Therefore, frequency will be measured in second inverse, that is reciprocal of second. Now, 1 second inverse is equal to 1 hertz. Hertz is the name of a scientist. To honor the scientist who has done a lot of work on oscillatory motions, the frequency unit is named as hertz, and it is written as Hz, capital H, not small h. Hertz, when you write the symbol, it will be represented by capital H and small z. Okay? But when you write it in words, that is full words you write in spelling HERTZ, it has to begin with a small letter, not with a capital letter.
Ma'am, would you like to tell us why? Because generally in English, when we use the name entirely begins with a capital H. But here you're saying that the unit begins with small h.
Right, you are right. In English, the name of a person will always begin with a capital letter. But in our system of units, there is a convention that all units which are after the name of a person, when their symbols are used, it will always be written in a capital letter. But when it is written in total, that is incomplete in spellings, we are not writing the name of a person, we are writing a unit. So we will start with a small letter only.
Is it the same with every unit?
With every unit. Like unit of force you must have seen in earlier chapter is Newton. So Newton, when you write a force of 5 Newton is acting on a body, so we'll write 5 and capital N. But if we write the complete word Newton, then it will be small n. It will begin with small n, Newton. Okay, that is our convention. It has been internationally followed.
Okay.
Okay. Now, so circular motion is not an oscillatory motion. Circular motion is periodic. Okay. Is there some link between circular motion of a particle and oscillatory motion? That is what we want to see now. What is oscillatory motion? And another thing is, what is simple harmonic motion? That will be in the next topic. Which motion you call as a simple harmonic? Now, simple harmonic motion is the one which is oscillatory. That is, it repeats itself after a certain interval of time. Body moves back and forth, and then it has only single frequency. It doesn't have a combination of frequency. It will have only a single frequency. Okay. Now let us see what is the relation between circular motion and an oscillatory motion. Okay.
Okay.
Now we have here, I am showing you a diagram. We have taken the case of a particle P which is moving along a circular path. Here I will draw the diagram on the paper. You have a circular path. First of all, we have to fix our coordinate system. So I draw the two diameters of the circle, where the points where these diameters are intersecting, that has to be the center of the circle, O. Okay. Now initially, to start with, suppose our particle was here at this point P at time t is equal to 0. It begins to move. As it begins to move with a certain frequency, okay, say linear frequency nu, but angular frequency is described by the symbol omega. Omega is written as W like this. This is the symbol for omega. So after some time, it goes to the position P dash. So the position vector OP describes an angular motion of angle theta here. Okay. So theta will be equal to omega into t, that is angular velocity into time, because distance covered is speed into time always. So angular velocity into time. Now as the particle goes from P to P dash, let us see in which direction does the foot of the perpendicular moves when the particle is moving along the circular path. If I draw perpendicular from P dash onto x axis, this is where it falls at the point M. It started from the point P, it has come to the point M. After some time, the particle goes to this new position now, as it is moving in the circular path. This is the position vector now. Angle has changed, it has increased. Draw the perpendicular. It comes to this position. Okay?
Okay.
When it goes to this position, draw the perpendicular again. It comes to this point. Draw the perpendicular, it falls at O. As the particle has moved along the circumference of the circle, the foot of the perpendicular has moved from point P, that is on the circumference of the circle, to the center of the circle. Now, when the particle continues its motion and goes to this new position, this is the position vector. Draw perpendicular. It goes to this position, that is now it is going away from the center. It goes to this position. It comes here. It goes to this position. Perpendicular falls here. Ultimately, the particle comes to this position, that is diametrically opposite to P. Okay? The particle started from P, went from P to O, then from O to Q. Now, when it comes to the third quadrant, it comes here. Draw perpendicular on x-axis again. It falls at this position. When the particle comes here, draw perpendicular again. It comes to this position. When the particle comes here, draw perpendicular. It comes to this position. When the particle comes to this point, the perpendicular will fall on the center again. When it comes to this side now, while continuing its circular motion, draw the perpendicular on the x-axis again. It falls here. When the particle comes here, perpendicular falls here. So you see, by the time the particle completes one circular path, one rotatory motion, the foot of the perpendicular moves from P to the center of the circle, from center to the point Q, from Q back to O, and from O again back to P, and one oscillation is completed. So the foot of the perpendicular is executing here oscillatory motion, whereas the particle itself is moving a circular path.
And ma'am, how much time does a particle take to complete this one circle?
That is equal to one time period.
Okay.
One time period, suppose time period is 2 seconds, this particle has completed the circular path in 2 seconds, the oscillatory motion will also be completed in 2 seconds. Okay. Now, this is we have taken on x-axis. Similarly, we can draw perpendicular on y-axis and see that will also execute the oscillatory motion.
Okay.
Now, if I take another, I draw another diagram now on this sheet. This is the path the particle is undergoing, and these are the two axes. This is the center of the circle. Okay. Suppose at some point of time the particle was at P, at time t. So what will be the length of this OM? From P I draw a perpendicular. Okay. On the x-axis, this angle is omega t, theta. So how much will be OM? This we can use our trigonometry. Our trigonometry says that we need to find the base here, and base comes in cos theta. Cos theta is, that is cos omega t is base upon hypotenuse, that is OM upon OP. OM, we want to find out how much is the displacement the particle has moved, is equal to OP cos omega t. Now OP is nothing but the radius of the circle. We can represent this by A, capital A. There is no rule whether it is capital A or small a, but we always prefer capital A here because small a we use for acceleration. So that is why we are not using small a here, we are using capital A. But there is no hard and fast rule. This is equal to A cos omega t. That means the displacement of the particle from its mean position, the mean position means the point about which the particle is oscillating, is OM, which is equal to A cos omega t. Okay. If we are considering the projection on x-axis. Now, if we take the projection on y-axis, then I have to draw perpendicular on this side. ON. How much is ON equal to? ON will be same as PM here. That is, it will be A sine omega t, which you have already done in resolution of vectors mein. Or it's a simple trigonometry. This is omega t. Perpendicular upon hypotenuse is sine theta. That means PM upon A will be sine omega t. Therefore, PM will be equal to A sine omega t. So, whether we consider the projection on x-axis or y-axis, we will see that will be represented by a trigonometric function. Now, you know that trigonometric functions are also periodic. They repeat their value after 2 pi. They have a period of 2 pi because in one rotation, particle will complete one oscillation, that is angle around a point. And angle around a point is 2 pi radians or 360 degree. That means simple harmonic motion can be represented by either A sine omega t or by A cos omega t. Now here A, as I told you, omega is the angular velocity. That means angular velocity is angular displacement per unit time. Angular displacement means theta upon time, t. So what will be its SI unit? For angle, the SI unit you know is radian, and for time is second. So therefore, SI unit of angular velocity will be radian per second. Okay. Now, as this diagram shows here, the same thing what I explained you, that the foot of the perpendicular OP is given by x is equal to A cos omega t. But if you draw that foot of the perpendicular on y-axis, that will be given by A sine omega t. Okay. The general equation for a simple harmonic oscillator is either x is equal to A cos omega t or y is equal to A sine omega t, depending upon from where the body starts oscillating. If the body starts oscillating from extreme position, then we use cos omega t. If the body starts from mean position, then we take A sine omega t. You have to notice this point. If the body is starting its oscillation from extreme position, we will use cos omega t. If it starts oscillating from mean position, we will take A sine omega t. Here, x and y represents the displacement of the oscillating body and A represents the amplitude, that is maximum displacement of the particle from its mean position. In our example of circular motion, it was equal to the radius of the circle. Okay. Now here, there is another name coming up, that is called phase. You must have heard about phase earlier also. Phase in different contexts has different meaning. You know phases of moon. That is one way. In what phase of life you are. That tells you, that is whether you are in childhood or you are young or you are adult. Similarly, here in simple harmonic motion, phase gives us where is the particle during oscillation and in which direction it is moving. Phase help us to know the displacement and direction of motion of the oscillator. And in this figure, in this expression, you will find y is equal to A sine omega t. That argument of sine omega t, that is the phase. So if you just want to find out the phase of a particle from the expression, just see how much is the angle along with the sign that is written there. That is omega t is the phase. It could be sine or cos. Whatever is the argument of sine or cos, that is the phase, and this will tell you where is the particle and how much, in which direction it is moving. Okay. Now what is initial phase? see that actually the particle may not always start either from mean position or from extreme position. The particle may start, say for example, if you take the case of a swing mean you may not pull it to the side, okay. If you take the case of a swing, you may not pull the swing to the side and leave it. From the center itself you might push it. So that means its phase is different. So if the particle at t is equal to 0 is neither at mean position nor at extreme position, then from where it starts, that is called its initial phase. In the case of circular motion, if the particle doesn't start either from here or from here, the particle starts from here only. At t is equal to 0, it was at this position. From here it starts moving. At time t, it covers this angle theta. Then this initial angle which it makes, that is at t is equal to 0, whatever angle it makes with the x axis, that is it's called initial phase. So its position vector makes an angle phi with x axis, then phi is called the initial. This is phi. So it started with initial phase phi. It did start either from extreme, because if you draw perpendicular from here, it falls somewhere here. The particle started oscillating neither from extreme nor from mean. This is extreme and this is the mean. It started from somewhere in between. That is what is called as the initial phase. So initial phase is also an angle. Okay. Now it could start oscillating either phi radians above axis or phi radians below x axis. Depending upon the case, it will be either positive or negative. So we always write the general equation of simple harmonic motion as y is equal to a sine omega t plus minus phi. Okay. For the derivation for purposes, we will not consider phi. We will take phi is equal to 0 for simplicity, for simplifying our expression. But in some expressions, you will find the equation as y is equal to a sine omega t or a cos omega t plus minus phi. Okay. Now let's see this question. This question says a body oscillates with simple harmonic motion according to the equation, and now bracket it is written in SI unit. That means all physical quantities here are in SI unit. Okay. So here it says, now you have to find the amplitude, the angular frequency, the time period, and also find the displacement at 1.5 second. So what we do is, to solve this problem, we just compare this equation with equation of a simple harmonic oscillator. This is given in terms of cos. So we'll write x is equal to a cos omega t plus minus phi and compare it. Now in place of a in this equation we have 5. Therefore, the amplitude A of this oscillator is 5 meter because we are considering SI unit. Okay. So in this case, amplitude is 5 meter. Now how do you find out omega? Omega and initial phase. Let's first find out the initial phase. Initial phase is when you compare it with a cos omega t plus minus phi. So what do you have in place of phi here? We have plus pi by 4. So phase of this particle is plus pi by 4. Okay. Now here x was equal to 5 cos 2 pi t plus pi by 4. And our general equation is x is equal to a cos omega t plus minus pi by 4. So when you compare these, a is equal to 5. This is phi actually. So your phi is pi by 4. Okay. And what will be the unit for phi? It's an angle, so it will be radian. Okay. Now next question is how much is angular frequency? If you compare here, angular frequency omega will be equal to 2 pi radian per second because it is angular velocity. Okay. So now you know initial phase, you know angular velocity omega, you know amplitude. Now you have to find out the displacement of the particle at t is equal to 1.5 second. So for that, what you do in the given expression, x is equal to a cos, that is 5 cos omega t, just substitute for all the values. So what is here? X is equal to 5 cos 2 pi, t is 1.5. So into 1.5 plus pi by 4. So this comes out to be 5 cos 3 pi plus pi by 4, that is 5 cos 13 pi by 4. 13 pi by 4 will have a value of minus 0.707. So the displacement is minus 3.535 meter. This is one of the question which you can easily solve once you know the equation of a simple harmonic oscillator. Okay.
Ma'am, what's the value of units in physics?
The value of?
Units, if we skip writing meters at the end.
Okay. That is, whenever we write, see whatever physical quantity we write, if we write x is 5 meter, that means meter is the unit of length. That means that quantity x is length. Unit is that thing in which we, see when you want to measure something, in order to measure, you have to compare it with something. Suppose you want to measure the length of a room. How do you measure the length of a room? You take something, say a meter scale. Then you keep it against the side of the room. See how many times you have to keep it. Suppose 5 times you keep it and the length of the room is covered. Then I will say that the length of this room is 5 meter. This meter with which I compared the length, that is called the unit. Unit is the basic standard with which we compare a quantity to measure. Okay. Suppose you want to measure the weight of the sugar which you have. You keep sugar on one side and then you keep the weight on the other side. Then you compare the two.
Right.
So then you say, if on this side you keep, say, 1 kg weight, on this side is the sugar. And the pan is balanced. So we'll say that the weight of the sugar is 1 kg. That kg weight which you have kept in the pan, that becomes the unit.
Okay.
The standard with which a quantity is compared in order to measure it, that is called its unit.
But if a student skips it, so will the marks be deducted?
Will definitely be deducted. Oh. See, whenever you have a numerical problem, marks are always divided. If suppose a numerical is for 3 marks, half a mark is for the formula, half a mark is for the substitution, then 1 mark is for the calculation, and then 1 mark is for writing the correct result. That is, the correct result means the correct unit also. Oh. So in every numerical, half a mark is assigned for units.
Okay.
So units are very essential. Without unit, your answer will not be considered perfectly correct.
Okay.
Okay now. Now, how do you find out the velocity of a simple harmonic oscillator? As I told you earlier, in the case of a simple pendulum, when you pull it to the side and then you leave, its velocity begins to increase. Comes to mean position, velocity becomes maximum. Overshoots it, goes to the other side, velocity becomes 0 again. Now that means velocity is not constant. So how do you find out the velocity of the simple harmonic oscillator? This you can see here. Velocity can be determined as by rate of change of position. The position y is given by y is equal to a sin omega t, suppose. It could be a cos omega t also, but I have taken here a sin omega t. And I have taken phi to be 0 for convenience. So when I differentiate it, v is equal to dy by dt. So dy by dt means you are differentiating y with respect to time. Now differentiation you have done many number of times so far, but still I will tell you how do you differentiate a quantity. See, y is equal to a sin omega t. Okay. So v, which is equal to dy by dt, will be equal to d by dt of a sin omega t. Okay. A, the amplitude is always constant, that is not going to change with time. So this constant we can keep outside the sign of differentiation, a. Now the derivative of sine, differentiation or derivative are the same thing. The derivative of sine theta is cos theta. So it is cos omega t, theta is omega t. And then you find out, you multiply this by omega. You differentiate omega t, that is into omega. So this becomes a omega cos omega t. This is what you have in the slide. So, when you find derivative, first the derivative of the trigonometric function and then for the argument. Argument is omega t. Okay. So, the velocity of a simple harmonic oscillator at any point of time is a omega cos omega t. Okay. Now, are the velocity and displacement having the same phase? We started with a sin omega t, but what we got finally is a omega cos omega t. Now, cos omega and sin omega, you know, they do not become maximum at the same time. Sin 0 is 0, but cos 0 is 1. That means they have a phase difference of pi by 2. Phase tells us how much, when do they become maximum? If they become maximum at the same time and they are moving in the same direction, that means their phase is same. If they do not become maximum at the same time, that means they have a phase difference. Now, one is a sine function, other one is a cosine function. Sine and cosine have a phase difference of pi by 2. So, this can also be written as V is equal to a omega sine omega t plus pi by 2. So, phase of displacement is omega t and phase of velocity is omega t plus pi by 2. So, velocity has a larger phase, that means velocity is ahead of displacement. Okay. There is a phase difference of pi by 2 between displacement and velocity. Okay. Now, what is velocity? Amplitude. So far you have used the word amplitude. Amplitude means maximum displacement from mean position. If it is displaced by 2 centimeter, then we'll say maximum displacement is 2, so amplitude is 2 centimeter. But what is velocity amplitude? Now, you can draw a parallel here, as amplitude is the maximum displacement. So, velocity amplitude will be the maximum velocity of the simple harmonic oscillator. And you know that the sin theta or cos theta has a maximum value of 1. If V is a omega cos omega t, therefore, velocity amplitude will be a omega. And what will be its unit? Its velocity, same as for any velocity, that is meter per second. Okay. Now, let's write velocity amplitude or velocity in general in terms of displacement. We wrote it in terms of time. V is equal to a omega cos omega t. That was in terms of time. Now, we will write it in terms of displacement. See here, V is equal to a sin omega t. Okay. So, which is V will also be equal to, Y is a sin omega t. So, velocity is derivative of Y, dy by dt, which came out to be a omega cos omega t. Now, you know what's the relation between sin theta and cos theta? Sin square theta plus cos square theta is 1. Therefore, you know cos square theta will be equal to 1 minus sin square theta. That is what we are using here. So, we are writing V as equal to a omega cos theta, we are writing 1 minus sin square theta, that is 1 minus sin square omega t raised to the power half. Okay. Now, here what you can do is you can take a inside. When you take a inside, what does it become? It becomes V is equal to, see on the board here, V is equal to, you take a inside the bracket, the outside the bracket you have a raised to the power half. So, it will become a square here, because when you take it outside, you have to find its square root. So, it will become a minus a square sin square omega t raised to the power half. Now, this term a square sin square omega t is nothing but y square. So, omega into a square minus y square to the power half. So, that is how you can find out the velocity of the simple harmonic oscillator at a given displacement. V is equal to omega a square minus y square raised to the power half. Okay. Now, let's try to do a numerical problem on this also, on velocity. Find the time and position where the velocity of a simple harmonic oscillator will be half of its maximum value. Now, as you know, y is a sine omega t. So v will be a omega cos omega t. We want to find the time when velocity will be half of maximum velocity, and maximum velocity is a omega. So therefore, we will substitute for v as a omega by 2, half of maximum velocity. This is equal to a omega cos omega t. A omega gets cancelled. So you get omega t is equal to, cos omega t is equal to half. That is, cos theta is half. You know, cos theta has a value of half at 60 degree. That is, omega t is equal to pi by 3, which is nothing but pi by 3 radian means 60 degree. That means the time, which will be now pi upon 3 omega. Okay, and omega you know is 2 pi by t. You have already done in earlier chapter. So the time here comes out to be t by 6, 1/6 of the time period. Have you noticed something here? See, when a simple harmonic oscillator is oscillating, okay, please focus on the board here. It is oscillating from one position to another. Suppose it starts oscillating from here. It starts at t is equal to 0. It moves this side, comes to this extreme position, comes back. So that is one time period. So time taken to go from A to B to C. A to B is 1/4 of the time period. B to C is 1/4 of the time period. C to B is again 1/4 of the time period. B to A is 1/4 of the time period. Okay. So from one extreme to mean it take t by 4 times. But see, the velocity velocity changes from 0 to maximum here. It is 0 here, it is a omega here at mean position. But the velocity does not become half at t by 8, because half of t by 4 is t by 8. Velocity become half only t after a time of t by 6. That means the velocity is not changing uniformly. It is not changing at a constant rate. That is what you have to keep in mind. In a simple harmonic oscillator, velocity is not changing at a uniform rate. Okay. Now, see in case of displacement, how do you find out the displacement when the velocity becomes half? Now we'll use the other formula. V is equal to a omega into 1 minus y square by a square raised to the power half. Substitute the value. A omega by 2 is equal to a omega into 1 minus y square by a square raised to the power half. So you get y square by a square is 3 by 4. That means y will be equal to, if you solve it, root 3 by 2 times amplitude. That means 0.866 times the amplitude A. So it doesn't become half in the middle because it is not moving with a uniform change in velocity. Okay, another question. The displacement of a particle executing simple harmonic motion is represented by the displacement function xt is equal to a cos omega t plus phi. If the initial, that is initial means t is equal to 0, position of the particle is 1 centimeter and its initial velocity is omega centimeter per second. What are its amplitude and initial phase angle? That means you have to find phi and you have to find out A. What is given to you? You have been given the displacement at t is equal to 0. So in the given equation, we'll substitute the values. X at 0, t is equal to 0 is given to us, is a cos phi, because omega into 0 will become 0. And x at 0 is given to be 1 centimeter. You have to keep track of the units here. Here the quantities are given in centimeter, that is CGS system. 1 centimeter. And velocity will be given by, we can differentiate, minus a omega sine omega t plus phi. So thus now substitute for t is equal to 0 here. V at 0 is equal to minus a omega sine phi because t is 0. This is given to us as omega. Now we can just divide equation 1 and 2. If we divide equation 1 and 2, a and a gets cancelled. Okay, I am dividing equation 2 by 1. So we get cos phi by sin phi by cos phi, which is tan phi. Okay, we get tan phi is minus 1. Tan phi minus 1 means phi is minus pi by 4. Okay, now you have to find amplitude. In equation 1 you can substitute. X0 is a cos phi, that is 1. So a cos pi by 4 is 1. So you get a is equal to cos pi. Cos pi by 4 is 1 by root 2. So root 2 goes to that side. It becomes a is equal to root 2 centimeter. So you have to write the units here as centimeter, and whenever you read a question, read it very thoroughly and see what is the system of unit the question demands. If it demands SI system, give your answers in SI. If it is given in CGS, it is better to give in CGS only. No need to convert it. Okay? Now.
Okay, ma'am, we don't have much time left. So I would request you to just finish this answer.
Okay, I'll just finish this answer now. So whenever you have to study the simple harmonic motion, you have to keep this answer. Of course, this answer is complete by now. Now, this topic I will now conclude. Whenever you have to study simple harmonic motion, first study what is simple harmonic motion, what are the characteristics of simple harmonic motion. That of course we still not have completed. That we will be doing in the next class, which will be in the coming time, in this month only. That is why I called this as SHM part 1. So we have not yet completed even kinematics of simple harmonic motion. Velocity part we have done. Next time we will do acceleration of a simple harmonic oscillator, then the characteristic of a simple harmonic oscillator, then we will study about the dynamics of simple harmonic oscillator and some examples of simple harmonic oscillator. That will complete the basics of this chapter, and then you have to practice lot of numerical. On every problem, on every formula, you must complete at least 5 questions and solve all examples of NCERT and all back questions of NCERT. The questions which I discussed here are mainly from NCERT. Okay? Thank you very much.
Thank you. Thank you so much, ma'am, for the advice. And I'm sure the students who are watching this program, they are going to practice a lot so that they get the idea, they get to understand the topic very well. Thank you so much, ma'am, for being with us. It was a pleasure having you.
Thank you. Ayush.
Thank you. Thank you to all the viewers as well for being with us today. I really hope that you enjoyed this program and you enjoyed the topic. So if in case you have missed watching it, you can watch it again on our YouTube channel, that is NCERT Official. Anytime, all you need is an internet connection. That is it. Let me please thank our sign language interpreter as well, Naina and Dharna, for being with us and interpreting each and every word in sign language to all of you. Thank you once again to all the viewers for being with us today, and don't go anywhere because our next program is a maths program and which is just going to come up. The topic that we are going to discuss is vector algebra part 2nd, and this is for all the students studying in class 12th. So stay with us and keep your questions ready. Thank you once again. Have a great day ahead. I'm Tanvi Khurana and I'll take a leave of you. Namaskar.